Today, on how it's made. Scalpels. On the cutting edge. Oil paints. We'll give you the broad brush strokes. British police helmets. Making them is really old hat. And ice axes. Our report on these mountaineering tools is a real cliffhanger. The scalpel is the surgeon's trademark tool. Its short blade is razor sharp and designed to slice swiftly and cleanly through skin and what lies underneath. This surgical knife may be a simple instrument, but using it requires years of intensive training and steady hands capable of great precision. They make scalpel handles from rods of stainless steel. The blades are made either of carbon steel or stainless steel. They're sterile and for one-time use only. The blade steel is extremely thin, less than 0.4 millimeters. It arrives at the scalpel factory in coiled strips. The first machine feeds the strips into a press. A die inside punches out unfinished blades, called blanks. Blades vary in size and contour, but they all have the same slot in the center for attaching the handle. When you flex a blank, it bends entirely out of shape, so the next step is to temper the steel. The blanks pass through a furnace for about 30 seconds. The heat alters the molecular structure of the metal, hardening it. Now the blank has the flexibility a scalpel blade requires. From the furnace, they move through a punching tool that pops them from the strip. The separated blanks stack on a peg. A worker now takes each stack, threads a metal ring through the slots to keep them together, then sends off the blanks for surface polishing. That will restore the metal's original sheen, which the heat treatment dulled. After polishing, workers visually inspect every blank, discarding any defective ones. They transfer the blanks from the ring to a metal rod, using a gauge to measure out the right number. From here, they mount the rods onto grinding machines. Each one picks up a blank with a magnet, then places it in a holder. The holder runs the blank against a wheel coated in diamond particles, a powerful abrasive that smoothly wears down steel. The wheel shapes and sharpens a cutting angle, transforming the blank into a blade. As the blades come off the grinder, they cling together because the magnet that fed them into the machine magnetized them. To cancel this effect, a demagnetizing machine passes an electromagnet behind the stacks of blades. After a thorough cleaning in ultrasonic cleaning tanks, the blades move on to final inspection. Workers wear rubber covers to protect their fingers and keep the blades clean. They carefully scrutinize the cutting edges, discarding any blade that's less than perfect. Each and every blade passes through 2 different inspectors. In the packaging department, the first machine covers each blade with a brown paper strip that contains an anti-corrosion chemical. This provides extra protection against rust. The next machine slips each blade into a foil packet, then cuts the connected packets apart. Each packet bears the blade model number and a tracking code. As the blades come off the packaging machine, an inspector does one last quality check. Then he counts the blades and boxes them. Of course, it's critical that surgical blades be sterile, so the boxes go into a cobalt radiation chamber for about 6 hours, obliterating any contaminants on the blades inside. When the boxes exit the chamber, they're hospital ready. In the operating room, it's simply a matter of sliding the blade onto the protruding part of the handle called the bayonet. Like blades, scalpel handles also come in different shapes and sizes. Surgeons optimize their dexterity by choosing the handle that's the best fit for their hands and the best suited for the procedure those hands are performing. Making oil paint dates back to ancient times when people mixed minerals with wax or oil. In the 1400s, they refined the process, discovering that linseed oil was ideal as a pigment binder because it allowed blending and glazing in layers. Hundreds of years later, the colors in those paintings are still vibrant. Today, many oil paint pigments still come from natural sources. The rest are synthetically made. Both types are sold in powdered form to factories that manufacture artistic oil paints. Cuttlefish ink yields brown pigment. Lead produces a specific yellow, and mercury ore a particular red. In the past, pigment also came from stones, tree bark, plant gum, ground-up glass, even arsenic. The company's research laboratory spends about 2 years developing a color recipe. A chemist mixes specific amounts of linseed oil and pigment in a machine called an automatic muller. It rubs the ingredients together, dispersing the pigment particles throughout the oil. For each sample, he alters the formulation slightly in search of the perfect result. The research team compares the resulting colors and selects the best one. Workers pump the amount of linseed oil specified by that formulation into a mixer. Then they add the precise pigment amount. Most colors are made with just one pigment. The formulation stipulates the precise mixing time and speed. Now they ladle the mixture into a mill. 3 dispersion rollers rub the ingredients between them, separating pigment particles and coating them in oil. The recipe specifies how much pressure the rollers apply, how fast they turn, and for how long they work the mixture. Milling can take hours or even days, depending on the pigment texture. The quality control lab takes samples from each batch coming off the mill and subjects them to a series of tests. Technicians scrutinize paint from both sides of the mill to ensure it's processing the mixture evenly. First, a spread test. They place a heavy brass weight on a blob of paint for a prescribed period of time. Then they evaluate the volume of color and measure the distance it spreads. If it doesn't spread far enough, they mill the batch some more. Next, a dispersion test. The markings on this gauge indicate the size of the paint's particles in microns, millionths of a meter. If the particles are too big, the paint needs more milling. Finally, they time how long it takes the paint to dry to the touch. Each color has a specified drying time, ranging from 2 days to 2 weeks. The factory produces a labeled chart to display its 120 paint colors. Workers brush each color onto primer-coated paper. When the paint dries, they cut each bar into rectangular swatches called chips. Workers assemble the chart using this mounting machine. The bottom has a section for each color. The top holds a cardboard chart that has information about each color. After loading stacks of chips and coating the chart with glue, it's just a matter of mating the top and bottom of the machine. A chip for each color adheres to its designated spot on the chart. Back on the production line, the factory packages one color at a time in toothpaste-style tubes with a twist cap. Once the labels go on, the tubes make their way to the filling machine. There, the tubes are aligned for closure. A nozzle squirts in the paint, then clamps flatten the end shut. A roller folds over the edge to strengthen the seal against squeeze pressure. And these oil paints are finally ready for their brush with frame. British bobbies are used to standing tall because of their distinctive helmets. British police helmets are approximately 30 centimeters high. The rounded shape fits snugly to the head, but even so, they still add quite a bit of height to the bobby, and that can't hurt when you're staring into the face of adversity. Times change, but the bobby's helmet doesn't. It's looked the same for a century and a half. Today, they use a metal mold to replicate it in fortified plastic. The mold descends into an oven. A worker places a sheet of plastic overhead. He lowers the lid and slides a heated cover over it. It takes a couple of minutes for the heat from above and below to soften the plastic. The mold rises, and a vacuum below pulls the plastic to its shape. It hardens almost instantly, and he taps it with a rubber mallet to release the helmet shell from the mold. Using a bandsaw, he slices away the excess along the brim. And the helmet is now ready to be covered. For that, they use water-repellent wool. They cut out halves of the helmet pattern. And then they stitch the two halves together, making a raised seam, which gives the helmet a nicer line. They've coated the inside of the fabric covers with glue. They steam one. Moistening it will make it easier to work with. Then they brush glue all over the helmet shell. The fabric cover is now damp, making it easier to pull over the glued surface of the plastic helmet shell. They stretch it a bit so it fits tightly and doesn't buckle. Then, using a wooden tool, they smooth away any remaining air bubbles. They trim the brim to tidy it up. They sew rubber piping around the brim to reinforce it and give it a neater edge. They dip the prongs of some decorative metalwork in a chalky powder and use it to mark its positioning on the crown of the helmet. They drill holes where the prongs have left markings. Then they install the metal ornament, folding the prongs against the inside of the helmet. Next, they stitch together strips of tape, plastic, and foam to make the helmet's harness and chin strap. They fit the harness assembly inside the helmet and then secure it with a serious stapler. They wrap metal banding around the helmet and pin it down. The banding gives the helmet a snazzier look and hides the staples used to install the harness. The ornate helmet plate with the police force's insignia on it goes on the front. They tuck a sponge liner inside the helmet to protect the police officer in the event of a blow to the head. They punch ventilation holes in the sides. And now it's time to size it with a special gauge. They tweeze away any fluff and brush the wool to bring up the pile. Then they attach the label that signifies the product meets all the specifications. This police helmet is now ready to report for duty. It takes about half an hour to make one of these helmets, and it should keep a bobby on the beat in high style for quite a while. If you aim to conquer mountains, a couple of ice axes will come in handy. Ice axes were invented in the mid-19th century to help mountaineers get a grip on slippery slopes and pull themselves to the summit. They also use ice axes to stop a fall. They're really designed for peak performance. Talk about a steep learning curve. Climbing with ice axes takes a bit of practice, not to mention courage. To make an ice axe, they start with an aluminum rod. A powerful press bends it into a curve, giving it the basic contour of an ice axe. They flatten and shape the rod in 2 fiery dies. Each die has a top and bottom half, which they lubricate between forgings. The hot forging transforms the metal rod. And it starts to look a lot more like the shaft of an ice axe. The long ridges add strength to the metal, while other indentations mark where the attachments are to go. The forging creates a bit of a lip around the perimeter of the shaft. They call the success metal flash. It's easily sliced off by this press. This gives the ice axe shaft a cleaner edge and also makes it quite a bit lighter than the original rod, an advantage when you're toting it up a mountain. That aluminum rod has gone through quite a few stages, but now it has a whole new profile. This tub of vibrating ceramic cones will smooth the rough edges of the shaft. Here, a computerized drill makes holes in the recesses stamped into the shaft earlier. These holes will be used to attach other parts. The machine changes the drill bit to a circular blade. Then, guided by the computer, it cuts a slot for the ice axe pick. The saw moves to the other end and thins out the area where the handle is to be attached. Using another drill bit, it carves out a hole for the adjustable finger rest. Here we see a shaft that's been milled and drilled, compared with one yet to undergo the process. Next, the shaft gets a protective coating. Then it's time to bring all the pieces of the ice axe together. A worker applies epoxy to the inside of the rubber handle and slides it onto the shaft. The handle has an open end. He beads a little more epoxy onto it and then inserts a steel spike. He rivets the spike to the ice axe shaft. Once it's solidly anchored to the shaft, this spike will come in handy on that uphill trek. Plunging it into a snowy slope will help the climber maintain balance. Next, he slides a part called the adze into the slot in the head of the shaft. Climbers use the adze to chop steps in hard snow and ice. He secures the adze with nuts and bolts. And then he installs the pick. This hooked and jagged attachment will help get the climber up a mountain of hard ice. He tightens the bolts with a torque wrench. After all, a solid job here could be a lifesaver. Finally, he screws the adjustable finger rest to the shaft just above the handle. And now you have a tool that can help you scale new heights.